So last time we started talking about these clusters and groups of galaxies and how they can be used as independent cosmological probes to get things like dark energy equation of state and other cosmological parameters like measuring Hubble parameter and other things. So we'll not go into great details of how clusters are used for cosmology, but it is, along with type 1a supernovae uh, and other probes of large scale structure, an important cosmological probe. So now we'll actually go to other aspects of galaxy clusters. Galaxy clusters are one of the most important X-ray sources. So the first X-ray instruments that were launched in space, such as Einstein and Uhuru, one of the first X-ray instruments in space, were able to observe galaxy clusters in X-rays. Okay, not just AGN, of course, X-ray binaries were other X-ray objects, but galaxy clusters were also are important X-ray sources. So here is one of the nearest clusters called Coma cluster. And this is a surface brightness in X-rays. So this is an image of Coma cluster in X-rays taken with ROSAT Rontgen satellite on the left, and the right is from XMM Newton, which is a more recent X-ray telescope. So since this is so nearby, this is also very big on the sky. It's 2.7 degrees by 2.5 degrees. In comparison, the moon is half a degree in the sky. So it's like if you had X-ray eyes, you would see this guy like 10 times the size of the moon in the sky. So these are very big objects, especially if they are nearby. Very good question. We will actually talk about that, but since you raised this question, so they emit X-rays because their potential wells are deep, and the virial temperature of these potential wells lies in 10 to the 7 to 10 to the 8 Kelvin. So if you have hot gas, which is at keV to 10 keV, which is 10 to the 7, 10 to the 8 Kelvin, it sort of emits X-rays through free emission. Okay, you see like a central high surface brightness core, and then surface brightness decreasing, and then there is suddenly another increase in X-ray surface brightness. It's some sort of a sub-halo. So this is the primary halo, the cluster halo, and there is a smaller mass galaxy or a group which is falling through it. So it has its own sort of gas, high density gas associated with this dark matter halo. Right? So the galaxy clusters, most of the mass is in the dark matter halo, which you can sort of to 0th order approximate as spherical objects. Okay, and in this image on the right, this is actually zoomed in. So you can actually see this is 0.5 degrees and this is 10 arc minute, right? So 10 arc minute is like 1/6 of a degree. So right, and here you actually can see the the detector. On the focal plane, you have the detector pattern. So there are detection elements missing here. So you can actually see that pixelation here, right, these lines. Okay, and these are some of the other galaxies and some foreground objects, some background quasars and whatnot. The galaxy clusters, last time we saw that, they are over density of galaxies, especially red and dead elliptical galaxies in the sky. But they are also an extremely important source of X-rays. Okay, and here is another example. This is RxJ 13471145. This is one of the most luminous galaxy clusters. This is an X-rays. Okay, the color here is X-ray. So this is the brightest and dimmer. This is surface brightness again. This is a ROSAT, again a ROSAT image. Black color are galaxies in that region. So you can actually see there is no correlation between the X-ray emission and the optical appearance of the galaxy cluster. It's not as if with every galaxy you have a little excess of X-ray emission. That's not like that. The nice thing about X-rays is that if we know the emission mechanism, which in this case we know is Bremsstrahlung or free emission, then we can actually infer the properties of the emitting plasma. For example, what is the density and the temperature of the plasma that is emitting this X-rays. So these are surface brightness maps, but from modern telescopes like XMM Newton, what the primary observable that we have is the spectrum. So here, for example, are 3 model spectra. So these model spectra on the left are generated by a plasma model. So a plasma model is actually extremely simple. The other nice thing about X-rays is that it's mostly optically thin. That is, whatever photon is emitted, it sort of freely escapes. So it carries information about the mechanism that produces this light. Okay, so these are some model spectra in X-rays. So the x-axis here is energy in keV. So instead of plotting it as a function of hertz, you plot it as a function of energy. That's more common in X-rays. And on top, what we have is only free emission, right? Only emission from fully ionized plasma. So there are 3 lines there, and these 3 lines correspond to 1 keV, 3 keV, and 9 keV plasma. So the black one is 1 keV plasma, free emission from 1 keV plasma. This is from 3 keV plasma. This is from 9 keV plasma. This NH equals 0 per centimeter square. This is absorption. So 0 per centimeter square means that there is no foreground absorption that has been put in this plasma model. So this is generated from, these plasma emission models are extremely common. One of the most popular one is called APEC, APEC, Atomic Plasma Emission Code. I think that's what it is called. So this is just free. But if you also include free bound and bound emission. So free bound is electron is free and then it recombines to some energy level and then emits the photon. That's the free bound emission. And bound is just from higher level to lower level, an electron jumps in an ion and it emits radiation. So the bound transitions give rise to these lines. You can see very sharp lines here. Right? These are just like your hydrogen lines, Balmer lines, or H alpha line or Lyman alpha. These are lines in X-rays. Right? These come from highly ionized ions, especially from iron, because iron has a very high ionization potential, right? So even at such high temperatures of order 10 to the 7, 10 to the 8 Kelvin, it is not totally stripped, or the atoms are not totally stripped of their bound electrons. So that's why you have these lines. So if you are at low temperatures, this is the black line is what you get. So you see the background, there is a continuum, which is more or less like this one, right? But on top of that, you have these lines and other features like edges, which are embedded on top of that. Okay. And as you increase the temperature, as you go from 1 keV to 3 keV to 9 keV, a lot of these lines disappear. Can someone quickly tell why that might be? Why do the lines disappear? Like all these nice Forester lines just go away in the green curve. Simple answer, actually. Yes, most of these ions, for example, oxygen and carbon and whatnot, just got totally ionized. So there were no ions there which had bound electrons which could just come down and produce line emission. Okay. Now, the third panel here is again the same temperatures. Actually, no, this is only for 3 keV. So it's this one, the red one on top. And the same emission as here, except that here we have different levels of absorption by the foreground. So the hydrogen column density of 0, this should not be minus 20. This should be 3 times 10 to the plus 20 and 10 to the 21 per centimeter square. So what you see is that the soft X-rays, the lowest energy X-rays, are easier to absorb. So you see all this 0.1 keV emission is absorbed by foreground gas. So what you will see from an X-ray spectrum is something like this. It will have everything. It will have background continuum due to free. It will have lines and edges due to bound and bound free. And then it will have absorption due to foreground. So an observer will have to like model all these out in order to get the true spectrum from the galaxy cluster. And the other thing that we have to keep in mind is that galaxy cluster is a sphere, okay? And what you're observing is a circle. You're basically observing a projection of the sphere on the sky, which appears as circular, sort of, circular isophores. Okay, so for example, the inner region, if you're looking at the center of the sphere, you're not only looking at the central part, emission from the central part, but also emission from the outer parts, because right, that line of sight encounters plasma at all radii from the center of this galaxy cluster. So one has to be mindful of these projection effects in galaxy clusters. So this formula here, epsilon nu ff, is the formula for emissivity due to free emission. So the microscopic picture for Bremsstrahlung or breaking radiation or free emission is that you have ions or protons, and the electrons are sort of, electrons are coming, they get accelerated as they approach close to these ions and get deflected. Okay, and for that little time when they're close, one can use that impact approximation, right? That most of the collisions are small angle collisions. So the same sort of a formalism works here, and you can actually derive the spectrum of free emission, which goes like this. Okay, so the most important thing to remember is that there is this exponential cutoff at higher frequencies. You see this here in the spectrum. There is a cutoff at higher frequencies. That happens when h nu is of order kT. So that's why the higher temperature plasma has a cutoff at higher frequency or higher energy, right? H nu equals E. This is plotted as a function of E. The other thing to notice is that in the flat part of this, there is a frequency dependence here in something called the Gaunt factor. This GFF is a quantum mechanical correction to this classical formula. So the frequency dependence, except for this exponential cutoff, is rather weak. So you have a flat emissivity and then an exponential cutoff. Unlike a black body, where you have nu squared and then an exponential cutoff. So this is free emission. This is a thermal emission mechanism, but a thermal emission does not necessarily mean black body emission. This has to be extremely clear to you. Okay, thermal emission means that the emitting particles, emitting electrons, have a Maxwell-Boltzmann distribution function. That's it. Whereas a black body spectrum, to get a black body spectrum, you want the photons to interact strongly with the atoms which are producing them. So in that case, the photon which is produced sort of collides with the atoms of the medium, and the photon temperature and the plasma temperature is the same. Here, for galaxy clusters, I said as soon as a photon is born, it just leaves the cluster. It's optically thin. Okay, so there is a famous 6.8 keV line which you actually see here, even for the 9 keV plasma, which is a hydrogen-like iron. So you remove 25 electrons from iron so that there's only one electron left. And then the energy levels analytically, because it's just z squared dependence of En. So if z is 26, z squared is like about 500. Okay, so 500 times 13.6 eV brings you to keV. Okay, so that's why you have these emission lines in keV. Right. So these are called one zone models. These kind of models, because you are assuming that you have a uniform medium with a constant density and temperature. So one zone means there is no density profile or temperature profile. But the true spectrum, like a true galaxy cluster, will have a radial structure, right? It will have a high density at the center and low outside. So you will have to like break it down into several one zone shells and then deproject the emission. So there is technique for that, and people use this all the time. Okay, now these are again X-ray surface brightness contours of a few galaxy clusters and groups. And the top ones, the contours, so you can actually see these guys, right? These very strong local enhancements in X-ray surface brightness. These are point sources, right? And generally, when you're studying galaxy clusters, you want to remove the point sources. These can be like X-ray emitting stars, nearby stars, or they can be AGN or X-ray binaries. They're all strong point sources, X-ray point sources. So you remove them, but this diffuse emission is coming from this hot gas in the galaxy cluster, which is called intracluster medium. This hot X-ray emitting plasma in galaxy clusters is called the intracluster medium. And most of the baryons associated with the halo, with the cluster halo, are in this hot X-ray emitting plasma and not in the stars, right? Galaxy cluster has thousands of galaxies. If you add the mass of all the stars in those galaxies, it's only about 10% of the total baryonic mass of galaxy clusters. So most of the baryonic mass, normal matter, in galaxy cluster is in this X-ray emitting plasma or the intracluster medium. Most of the mass, of course, is in dark matter halos, which provides this deep potential well. Now, the difference between the top and bottom surface brightness contours is that the top contours are almost spherical, circular, right? That means these are relaxed clusters. Yeah, they are not undergoing mergers or some very strong dynamical interaction. Whereas on the bottom here is actually the optical image. That's why you can actually see these galaxies and stars. Right? The contours are surface brightness contours. The bottom ones have contours which are not X-ray contours, which are not circular, and they are disturbed. Galaxy clusters formed from the mergers of smaller galaxies and groups. So mergers are very common in galaxy clusters. Okay, so when a cluster is undergoing a merger, you sort of disturb the X-ray emission in the galaxy cluster. So these are two unrelaxed clusters. These are relaxed clusters. Suppose you have such a galaxy cluster. So what from observations, what you can actually do is you can divide this into various zones, and you can get the spectrum from each zone. And once you have the spectrum, once I give you the spectrum, right, you can actually from the spectral lines and the shape of this exponential cutoff, you can tell what the plasma temperature is. And from the magnitude of emission, that is from the flux that you get, you can also get a sense of the density of the emitting plasma. You start from the outer region, okay? The outer, so if you have a spherical object, and if you're only looking at the outer parts, right, the projection effects are essentially not there. If you have the outermost shell, if you're looking through outermost shell, and if you assume that there is no foreground or background radiation along that sight line, you only get contribution from the outer shell. So you infer from the outermost shell, you infer the density and temperature of the outermost shell. Okay, then you go to the next inner shell, right? Now you know the emissivity of the outer shell. the next inner shell, you will get emission from the inner part, but also from the outer shell. But you already have inferred the density and temperature of the outer shell, so you can model it out. So basically, you move from outside to inside and try to get a density and temperature profile for galaxy clusters. Okay, so let me actually diagrammatically show it. This galaxy cluster. So what I'm drawing is these sort of a spherically symmetric galaxy cluster. Okay. Okay, and here is an observer. And so if you're observing this part of the galaxy cluster, of the outer part, you only get emission from this shell, right? You know, if you have like a beam which is only observing this part, and if you assume that the density and temperature, so basically if you have a density and temperature profile, the 3D profile, if you assume that this is like a step function or something like that, okay? And similarly, temperature is a step. So this has a constant density and a constant temperature. And for this outer part, right, you can get the spectrum. And from that spectrum, by comparing with this APEC model, you can infer, if you know the distance to this galaxy cluster, you can actually infer the number density and the temperature of this one zone plasma. This is like one zone. Now, once you know this, now you go to the second shell. Okay, here you have this new contribution, but this N and T is the same, right, as the outer shell. So, and from the spherical geometry, you also know the volume of this sky. So you can actually subtract these out. The contribution from the outer shell can be subtracted out, and you can actually get N and T for this, and so on. You can move inside, and you can peel off the outer contributions one by one. So that's how you can actually obtain, ultimately, after doing this exercise, you can actually obtain N as a function of R. This is the 3D profile, okay, and T as a function of R. This is sort of the idea. So from spectra, you can infer N and T if you know the distance. And a lot of times you know the distance because you know the redshift, you know the member galaxies or galaxy clusters. Okay, so if you do this exercise for this nearby Perseus cluster, this is how you get the temperature and even metallicity, right? So for example, here we have these lines. Okay, from the appearance of these lines, you can also measure the metallicity. If the plasma does not have metals, all these lines will be suppressed because these are coming from, you know, partially ionized oxygen, carbon, the more abundant ions, and iron. So if the metallicity is low, then these will be less prominent. So by comparing your emission from the model emission, where you sort of fine tune the metallicity, you can fit and get the metallicity of the plasma. So you can get metallicity profiles in the same way. So this is for a nearby cluster, which is extremely well observed. So you get this kind of a profile. So there is a large variation, point by point variation in the data. And the clusters need not be perfectly homogeneous, like in different directions. So this is northwest, east direction. So these are different directions, okay? And like two different directions can have slightly different temperature and density, especially at large radii. They are not as circular or spherical as at inner radii. Even the relaxed clusters have remnants of sort of their history in their outer regions. This is from Suzaku. These symbols are from an X-ray telescope, a Japanese telescope called Suzaku. And this is from Chandra. Chandra has a very high spatial angular resolution. So that's why the inner parts with high resolution you can actually do with Chandra. The outer parts, which is less, has lower surface brightness, you do with Suzaku. The problem with Chandra is that Chandra is in a large, the orbital distance from the Earth of Chandra is big, so it is outside Earth's magnetosphere. Basically it has a lot of particle background. So if you have very diffuse source of emission, it is not that great because it's dominated by the particle noise that it encounters in its large distance orbit. In contrast, Suzaku is in a low Earth orbit. It's sort of nicely shielded by the magnetosphere. So it is very good at detecting very diffuse X-ray emission. Okay. So galaxy clusters typically have this temperature maximum at the center. But you see, it's almost isothermal. The minimum temperature is 3 keV and maximum is 7 keV. Only a factor of 2 variation in temperature. These are basically isothermal. You remember the dark matter halos are to 0th order well approximated as isothermal spheres. So the depth of the potential well, the temperature associated with the potential well is almost isothermal, but it has a certain shape. And this is essentially that shape. So this is just, local phi. KT is, is proportional to the local potential phi. So the local potential has this slope, has this shape. And there are other factors which affect this temperature profile. So, for example, the accretion history of a galaxy cluster and whether the central plasma in a galaxy cluster is cooling. If the cooling time of the central galaxy is short, that is, cooling is important, then this temperature can be somewhat lower compared to a baseline model. So there are, there is a 0th order profile which is isothermal, but on top of that, the variations are due to the shape of the potential, the detailed shape, and the accretion history and cooling. Okay, the metallicity is high at the center because most of the star formation and so on happen at the center. Right, outskirts were less polluted, and the typical metallicity associated galaxy cluster at large scales is about 1/3 solar. That's the typical number that people assume. So remember, all the metals in the universe are produced in stars, right? So all these metals which are so far away in galaxy clusters and even in the intergalactic medium were once inside stars, right? So it's sort of like very surprising that now they are in, almost in the middle of nowhere. But once they were at the centers of these stars, and after supernovae and stellar winds, they were put out into the ISM and into the nearby circumgalactic medium, and these mergers of galaxies and then outflows launched by supermassive black holes, AGN, and supernovae just disperse them out. As I mentioned, galaxy clusters are really nice objects. They are accessible to observations from almost all wavebands, and being so big, they are easy to resolve. They're also reasonably bright in almost all wavebands. So you have exquisite observations, spatially angular resolved, beautiful observations. So one of such observations is shown here. The color here is the X-ray emission. So this is showing something called bullet cluster, and it's sort of a collision between two clusters. Okay. So this is the direction of collision. These are the intracluster mediums of the two galaxy clusters. So imagine two galaxy clusters and they just run into each other. This one has sort of, so basically there is this, the center of emission is offset from the center of symmetry of X-ray emission. It sort of shows that it has run into some very dense medium, and the X-ray emitting ICM has been drawn in some sort of a tail. Okay, it's sort of like a, it's like a bow shock, right? If you have an object moving fast through a medium, it causes this outer shock, a bow shock. It's sort of like that. Similarly, here also you have X-ray emission associated with the other galaxy cluster, the collision partner, that's also disturbed. Okay, so this is in X-rays. So naturally, if you have a collision, it will be disturbed. But what is shown here in contours is the reconstruction of gravitating mass through gravitational lensing. So how these green contours and white contours are obtained is the following. So you look at the background galaxies and look at their distortions, right? Because of gravitational lensing, the background galaxies shapes can be distorted, right? And we can actually model it, and the deflection and the distortion and all that depends on the total mass, total projected mass along the sight line. So by measuring the distortions, we can actually make these contours of constant mass surface density. So these are the contours of mass surface density. So you can actually see here in dark matter, there is no evidence. So, mass is dominated by dark matter. In dark matter, there is no evidence for interaction. They just pass through each other without really getting affected by. So if you were able to observe this collision between these two dark matter halos, they'll just go like this, and basically go like this forever. Now, of course, they will through dynamical friction, they will dissipate this energy, but on a much longer time scale compared to the time scale over which this energy in the gas component is dissipated through shocks and these strong interaction. So it's sort of like that the collision between the dark matter particles is elastic collision. It essentially does not dissipate energy, or dissipates it on a very long time scale. Whereas the collision between the gas, the ICM of the two galaxy clusters, is a dissipative collision. So it leads to shocks, gas compression, and radiation, and all that. So these two galaxy, the baryonic component can just sort of, after some time, it can just become a single ball, and will become spherical slowly on a short time scale after this collision and relax. So this is a very important example of the evidence of dark matter, right? It shows that in this collision there are two components: the mass component, which does not interact as strongly, whereas the baryonic component, which is strongly interacting. That's why this bullet cluster is given as a strong evidence for something like collision-less dark matter. And as I already mentioned, 85% of the mass is in the dark matter, and the rest is in this intracluster medium. Only 10% of the baryons are in stars. Another very, very important observable effect in galaxy clusters is something called the Sunyaev-Zeldovich effect, or the SZ effect. So the physics of SZ effect is the inverse Compton scattering. So you all are aware of Compton scattering, right? If you have an electron at rest, and if you shine a high energy photon on it, the photon gets scattered in some direction, but at energies of order the rest mass energy of the electron, the collision is not elastic, unlike Thompson scattering, in which Thompson scattering is also interaction of radiation or photon with electrons, but h nu is much less than mc squared in the Thompson scattering limit. So before and after the collision, the energy of the photon is more or less the same, right? But when h nu becomes comparable to mc squared, the photon loses its energy, and that's called Compton scattering. Okay. Now, in this classic Compton scattering, we take the electron at rest. So if the photon is losing energy, the electron will gain that energy. But if you have electrons which are moving, you can also have the transfer of energy in the other direction, right? If the electrons are moving, they can actually give their energy to the photon. If the temperature of the electrons is higher, for example, than the h nu of the photon, the electrons can give up energy to photons. This is called inverse Compton scattering. Okay, and the physics is the same. It's just like it basically is a mechanism of interaction between light, like electrons, and photons. So let's see. So this is sort of the picture of inverse Compton scattering. So you have this galaxy cluster. This is the hot cluster gas or the intracluster medium. There is a CMB. The CMB photons are coming in all directions. Okay. Now, at the nearby redshift, the CMB temperature is 3 Kelvin, 2.73 Kelvin. Now, the temperature of the galaxy cluster gas is 1 keV, right? So the energy per particle of ICM is much more than energy per particle of the CMB photons. So on average, the CMB photons can gain energy on interacting with this hot gas of electrons confined by this cluster potential well. This is the expression for average energy exchange between the photons and electrons because of this inverse Compton scattering in the non-relativistic regime, right? This is the like the keV or 10 keV plasma is non-relativistic because the electron rest mass is 0.5 MeV, right? So KTE is still much less than MEC squared. So this is a non-relativistic plasma. In that limit, in a single collision between electrons and photons, the average change in energy per unit energy of the photons, this small epsilon is the energy of the photon. So for CMB, this epsilon is like, corresponds to energy of 2.73 Kelvin, right? KBT. So whereas the electron is like a keV, so this epsilon can just be ignored compared to. So basically, in every interaction between an electron and the CMB photon, delta E by E for the photon will be 4 kT by mc squared. This is a result, that you get from averaging over all the angles and all that, and hopefully, this is done in Rybicki and Lightman. So I encourage you to check that out if you want to go into the physics of how this comes about. But this is the answer, that for every scattering between electrons and photons, delta E by E of the photon is 4 kT by mc squared. Okay, good. So what happens is the dashed line here is the black body spectrum of the CMB. So this is the CMB. Okay. Now the CMB is coming through the foreground clusters and the IgM and everything, right? When we are observing, the CMB is sort of, sometimes coming, interacting with these hot electrons in the clusters and whatnot. So some fraction of those photons can get upscattered, right? They can get boosted by delta epsilon by epsilon due to collision with an electron in the galaxy cluster halo. Now, the optical depth of a galaxy cluster to this inverse Compton scattering is very small. If you plug in the numbers, this Compton Y parameter quantifies this optical depth that I was saying. So what it says is about only 1 out of 10 to the 5 electrons, 10 to the 6 electrons will undergo this energy exchange with the electron. So what it does is for the electrons for the CMB photons which have gained energy from these electrons, the frequency has been shifted up for those interacting photons by this much. by 4 kT by mc squared. Delta E by E gets shifted up by 4 kT by mc squared. So that's indicated by these arrows. Right? This is shown like this is very exaggerated. What's shown here is very exaggerated. This will only happen for 1 out of 10 to the 6 photons. So this will be a tiny effect. But our precision with which we can measure the CMB fluctuations is very good. So this is still measurable. Okay. So the pristine CMB photon spectrum becomes something like this, shown in the black line. This is Compton scattering, and in every scattering process, the number of photons is conserved, right? Because it's not creating new photons or absorbing photons. It is just exchanging energy. So the area under, basically the total number of photons is the same, but mean energy of the photons has been increased because of this collision with hot electrons. Mean energy per photon has increased. So this is the Sunyaev-Zeldovich effect. So it's a small effect, but we can actually measure it, and it has this universal shape. The deviation from the CMB has this universal shape where this crossover. So this is the point, right, where the pristine CMB and the upscattered CMB has the same brightness temperature or the same I nu, right? Intensity, same intensity. This is 217 gigahertz. It does not depend on where the cluster is and whatnot, temperature of the electrons and so on. It's a universal number. It's 217 gigahertz, and this gx here, this function, is indicated here in the blue line here, and x is just this h nu by kt CMB. And this is a dimensionless frequency, so it has a universal shape, and this crossover happens at 217 gigahertz. This is that 217 gigahertz, and this shape is given as this. Okay, this is universal. The amplitude of this distortion of the CMB depends on this Compton Y parameter. It's proportional to this Compton Y parameter, which is nothing but the integral of electron number density kT by mc squared, which is nothing but this guy, right? 4 kT by mc squared is delta E by E. So it's just integrate. Basically, this is just calculating how many collisions on average will you have for a typical CMB photon. So this is called Compton Y parameter. And so what you do is you measure the SZ distortion by measuring the deviation from the CMB at different frequencies. So you basically try to map this out. Okay, and once you get the amplitude of this, you get Y. The amplitude of this effect is proportional to Y, right? The more the electrons you have, a higher fraction of the CMB photons will get upscattered. And also, the deeper the potential well, larger will be delta E by E, delta epsilon by epsilon. So this is what Compton Y parameter quantifies. And this comes from this, the physics of this is this equation, some sort of a Boltzmann equation for photons, right? Like how are photons sort of moving in the frequency space, right? So it's some sort of a approximation of the Boltzmann equation for photons, and in this approximation, it is called the Companys equation. So we'll not get into that, but that's really what gives you this Gx. But for this purpose, the shape of the Gx is what matters. This is sort of the answer. So at small x, this gives you a negative expression, right? So what it means is that at small frequencies, your intensity is suppressed. At high frequencies, your intensity is increased. Total number is conserved, but there is a gain in energy on average. Okay, so here is actually a real observation of this SZ effect. So this is a galaxy cluster April 2319, observed by Planck. Planck is a CMB experiment. This is at 44 gigahertz, 70, 100, blah, and blah. So what you see is, you see this, there is a deficit of brightness, or the brightness temperature or the antenna temperature is small below 217 gigahertz. At 217 gigahertz, there is no excess or deficit. As you go to higher frequencies, you have an excess. So this is the telltale sign, right? This is basically you're mapping out this this shape here, right? I mean, this is really amazing. This is one of the biggest discoveries in astronomy or like last 2-3 decades. You know, it's very, very important. It's also very practical. This is the way to discover the galaxy clusters at the highest redshift, right? In X-rays, where you're getting emission, the flux goes like 1 over distance squared. So if you put your galaxy cluster far and far away, these galaxy clusters in X-rays become really, really dim. So you cannot find them. But SZ effect is an absorption effect. It's an effect which is a scattering effect. And as long as you have a background CMB, which you always have, it does not matter really whether the foreground cluster is near you or far away from you. So you can actually detect galaxy clusters at redshift of order 1 or beyond from this effect, which is impossible to do in X-rays. Okay, very important effect. So this is the thermal SZ effect, right? Thermal SZ meaning if you have this galaxy cluster and if it is at rest, so let's say it's in the Hubble flow, it's not moving relative to the Hubble flow. In that case, you have an electron distribution which is sort of random. So some of the electrons are moving towards the CMB photon, some are moving away. And on average, there are equal number of those because, this is not moving relative to the CMB frame. It's in the Hubble flow. But even though the number of, so there will be some head-on collisions between electrons and protons and some tail-on collisions. In head-on collisions, you gain energy. In tail-on collisions, you lose energy. And the number of such collisions are equal. But in every, so there is a slight excess of these head-on collisions in which you transfer energy to the photons. Okay, so it's sort of like a second-order Fermi acceleration in some sense in cosmic waves. There is another effect which is called the kinetic SZ effect. So in that, if you have a galaxy cluster which has a peculiar velocity relative to the Hubble flow, in that case, on average, the electrons have a bulk velocity relative to the CMB. And on average, they sort of increase the wavelength or increase the energy of the CMB photons. So here in this dashed line is the signature of kinetic Sunyaev-Zeldovich effect. This is a little harder to measure and also very, it does not have this sort of a beautiful characteristic shape. The reason being you can have a cluster which is moving towards you, which is moving away from you, moving in some direction, and this change in intensity can be positive, negative. It does not have that beautiful characteristic shape. So just by CMB observations, you cannot measure it. You have to get an independent. So in that case, the equivalent parameter is n velocity in the line of sight sigma dl. And that velocity of the line of sight is something we have to measure independently. Okay, so most importantly, it's the thermal SZ effect which is easiest to measure. Okay, here is the demonstration of the power of this SZ effect. Right, so this X-ray brightness is dimmed, SZ signal is the same because it's based on scattering or absorption. So how do you get galaxy cluster sample at high redshifts? You just look at the CMB map. And if you look at that map at different frequencies below 217 gigahertz and above 217 gigahertz, and you see that there is a deficit at small frequencies and excess at small frequencies which follow this characteristic shape, you're pretty sure that there is a galaxy cluster sitting there. Now, once you do that, then you can actually know that there is a galaxy cluster there. Then you know where to point your X-ray telescope for a very long time in order to find the galaxy cluster. Right? You cannot just search in the blind with very long exposure times in X-ray. But once you know where this probable cluster is at high redshifts, you can actually look at it with a long time. So here are 1, 2, 3 galaxy clusters. Okay, this is at redshift 0.17, 0.54, 0.83, right? And this is the SZ signal. It's essentially the same. This, if you look at the same region in X-rays, is what you get in this inset. Very bright because it's nearby, manageable, but almost not there, right? Because the flux goes like 1 over distance squared. Right, this Compton Y parameter, this Y parameter that I mentioned, it's sort of like a integral of pressure along the line of sight, right? NE times T is proportional to the pressure of the intracluster medium. So this is like a local Y, like along a particular sight line. If you have a galaxy cluster which is resolved, you can get a value of this pressure integral along the line of sight. But if your galaxy cluster is not resolved at these high redshifts, they become small on the sky. Then what you get is a global, you don't have these individual sight lines. You have like an average Y. You don't have profile of pressure. You don't have a pressure profile. You have the integrated effect. And that is this capital Y. And that's like instead of a line of sight integral, it's an area and the line of sight integral, which is nothing but the volume integral, right? Area and the line of sight is just the volume integral. So that is just product of average pressure and the volume. And last time I mentioned briefly about this self-similar scalings of halos, right? The halo size goes like m to the 1/3. The halo temperature, the virial temperature of the halo goes like m by r, which is m to the 2/3. So pressure is like n times t, right? So n is universal. N is the same for all galaxy halos. But T is proportional to m to the 2/3, and volume is proportional to m. So this is proportional to m to the 5/3. So this is very, very useful for doing cosmology with galaxy clusters, because you can find higher and higher redshift galaxy clusters with this. So then there is Planck, of course, the all-sky CMB experiment. But to get higher resolution and to get individual cluster profiles, pressure profiles, you need a high resolution CMB experiment. And these Atacama Cosmology Telescope and South Pole Telescope are essentially doing that. They are looking at smaller parts of the sky, not the whole sky, but at high resolution. So you can actually measure out pressure profiles. Okay, so this is about like some of the probes. Now, galaxy clusters also have lessons for galaxy formation. According to classic galaxy formation theories, galaxies are hosted by dark matter halos, something like this, spherical halo. And matter along with baryons decoupled from Hubble expansion fall back, and it virializes at the virial radius. Now, if the gas, after getting virialized, is able to lose its energy fast enough, then all these baryons can form stars and hence galaxies. But if these baryons, which virialize, are not radiatively efficient, in that case, they'll form a roughly hydrostatic hot halo, like the intracluster medium. Okay, so you asked, like, why Why does it have X-ray emitting plasma? One of the reasons that galaxy clusters have X-ray emitting ICM and most of the baryons are in the ICM is because the cooling times of this virialized gas is very long. It's longer than the Hubble time. So the baryons can undergo a shock, and the shock gas does not cool efficiently. So it can just stay there. It can just get accumulated in form of this intracluster medium. But if you go to lower mass halos, the lower mass halos have shallower potential wells. They have lower virial temperatures. And at lower temperatures, you have a lot of ions cool efficiently, right? Because ions have these bound transitions, which can take away a lot of energy because of radiation. So, so the thing is, this is sort of the classic picture of galaxy formation within dark matter halos. If the gas which is virializing is able to radiate away most of its energy, then it will form stars and form galaxies. If it is not able to radiate efficiently, then most of these baryons will be in this diffuse X-ray emitting hot plasma. So the question is, how can we sort of predict the distribution of baryons as a function of halo mass? What is the fraction of mass in stars, hot gas, cold gas, ISM, blah, blah, as a function of halo mass and redshift, for example? So, even our Milky Way has sort of roughly a structure like this, that there is a disk and it has stars and gas, ISM. It's only like 10, 20 kpc, right? But it's surrounded by this circumgalactic medium, which extends out to 200 kpc, 10 times bigger than the size of the interstellar medium and star-forming disk. So this region has huge volume. Even though its density is very small, it has like factor of 10 in size. So in volume, it becomes 10 cube, 1,000 times higher volume. So it can actually store a lot of baryons, even though it does not emit much, even though it is almost imperceptible. But it can be very, very important reservoir of baryons and can control galaxy formation and everything. So, so this is how it sort of connects. The galaxy clusters are basically deep potential wells in which there is gas which does not radiate, cool efficiently. But if you go to like Milky Way mass halos or even lower, the virialized gas can actually very efficiently cool. And there is this whole literature in the last 20 years about this hot mode and cold mode accretion, hot mode accretion of baryons at large scales. Okay, and this is sort of qualitatively what I just mentioned. So for galaxy formation, what are the important physical components? One is, of course, the Hubble expansion. Second is self-gravity. The gravity has to pull in matter and force it to collapse. The third, and not so trivial component, is this radiative cooling. Right? All these atomic processes, transitions and all that, is what fundamentally governs galaxy formation. And the fourth one, which we'll actually come to, is something called feedback. Gas cools, but that cooling gas forms stars, feeds the supermassive black hole, and that can bring, put back energy into this intracluster medium or these atmospheres, and can control the inflow of cooling gas into the into star formation or black hole accretion. So it's sort of a feedback regulated system. That's the modern understanding, that the galaxies are self-regulated because of this interplay between cooling, gravity, and energy put back in by star formation and AGN feedback. This is actually a quantitative graph of what I was actually saying in words. So this is temperature, this is density. Once you have density and temperature, you can calculate the cooling time. Right, so if you have a little fluid element here, if it, if it is optically thin, it can, lose its energy. Even optically thick, it can lose its energy, but on a longer time scale, because photons do not just uh, leak out immediately. So the rate of change of internal energy due to cooling can actually be approximated as minus n E n I lambda t. Right? Cooling processes of the kind that we're talking about are two-body processes. Uh, you have protons or ions and electrons being accelerated by them. Right? So the radiation is proportional to n squared. Okay, so we can actually define something called the cooling time, right, which is nothing but the thermal energy of the system divided by this guy, right? E dot cool, Ne Ni lambda T. Right, so this is the cooling time. So if you're, so lambda, right, you see, there's a reason why we are sort of writing it in this form, n squared lambda, because this now is a part which only depends on temperature, not on the density. This is just a pre-factor which is sort of controlling for the density dependence. So if you plot lambda as a function of T, lambda is nothing but, so what are the units of lambda? It's erg centimeter cube per second, right? Because n squared is centimeter to the minus 6. You should, so this is nothing but rate of change of energy, energy per unit volume per unit time, right? So this has this lambda is the cooling function. What you're doing is you're just integrating over all the frequencies. How much energy does this plasma lose in total at a given density and at a given temperature? So this lambda T as a function of T on a log plot sort of looks like this. So, right. So at high temperatures, it's T to the 1/2. This is the free regime. And at low temperatures, it has these, it has this shape. So this is about 10 to the 4 Kelvin. This is about 10 to the 7 Kelvin. At about 10 to the 7 Kelvin, the plasma is more or less totally, fully ionized. So you're dominated by free radiation. Here at intermediate temperatures, you have, for example, oxygen or neon ions or the iron ions and, oxygen, helium and hydrogen, right? They get excited and they can take away a lot of energy. Okay, so this is lambda T. If you recall, there was this epsilon nu T, right? The emissivity of the plasma. This lambda T is essentially proportional to epsilon nu by n squared d nu, right? You're calculating how much energy does the plasma lose across all frequencies. If you recall, the epsilon nu for free was proportional to, there was a very weak nu dependence from the Gaunt factor, and then there is e to the minus h nu by kt, right? So if you and there was a 1 by, right, there was 1 over square root of t. If you integrate this over all frequencies, right, what you get is d nu, which is like lambda. You will get, right, when you do d nu of this, you essentially get kt in the numerator, because you're going from the cutoff, the exponential cutoff, it is at h nu of order kt. So the integral over nu will just pick out kt. So it's basically kt over square root of t. So this is proportional to square root of t. So this is what this guy is, right? So if you draw the plasma emissivity as a function of frequency, this has this dependence on t and nu, right? There's of course this n squared, which I'm just ignoring. So, right, so this is free, these are lines. Now at this temperature, below 8,000 Kelvin, the plasma is just too too cool for it to even excite hydrogen from n equal to 1 to n equal to 2. So even like Lyman or Baum, hydrogen emission gets suppressed at low temperatures. Okay, so that's why a lot of plasma likes to sit at these temperatures, because it can cool, but suddenly as it hits about 10 to the 4 Kelvin, it no longer is able to populate higher levels of hydrogen, which can take away the energy radiatively. So it sort of likes to sit there for a long time. So this cooling function is extremely important for galaxy formation. So for galaxy clusters, so if you have this kind of a shape, right? This part you can actually approximate as t to the -1 essentially. This is a very crude approximation. This is actually good. This is very good because this has bumps and wiggles and whatnot. So if you look at the cooling time, it was nkt 3/2 nkt over n squared lambda t, right? And this is proportional to t over n lambda. So if we are in the Bremsstrahlung regime, so in FF regime, this is T cool is proportional to T to the 1/2 divided by N. Recall, for self-similar models, N is constant. Density is constant across halos. So for massive halos, the temperature is higher, right? Recall, T is proportional to M to the 2/3 from this self-similar scaling. So for more massive halos, the cooling time is longer and longer. That's why the more massive dark matter halos have this gas which cannot cool radiatively so easily. So it just gets accumulated in the intracluster medium rather than forming stars and the galaxy at the center. On the other hand, if you are in this regime, if you are here, right, the cooling time in that case is proportional to T over N T to the -1. I mean, I gave you that crude approximation in that regime. That's proportional to T squared by N. As you go to lower and lower temperatures, this actually becomes pretty steeply decreasing with temperature. So lower mass halos with lower potential well depth, lower virial temperatures, gas is able to cool very efficiently. And a lot of that gas cools to form stars. Okay, so that's the 0th order understanding of coarse large scale galaxy formation. Now this is a plot of N and T. So once you know N and T, you know the cooling time, right? This curve here is the contour of cooling time is equal to Hubble time, right? You see this is so using that lambda T that I drew, you can calculate T cool, right? T cool is just nkt over n squared lambda T. If I draw that in this temperature density plot, I get this as this is the locus of T cool equals T Hubble. Okay. Now these regions with higher density than this contour will be cooling really crazy, right? High density gas has a short cooling time. So all this parameter space is very happy to form galaxies efficiently. But this parameter space is not. So this is where galaxy clusters lie, above this. So the gas does not cool within a Hubble time for galaxy clusters. Normal galaxies lie in this regime. Okay. And so there are these, this Jeans mass, which is indicated here, which you can actually take sort of as a proxy of the galaxy mass. So the galaxy mass between 10 to the 9 or even 10 to the 6 to like 10 to the 9 to 10 to the 12 solar mass guys, galaxies are very happily cooling. So this is the mass of the Milky Way halo. But if you go above it, you are in this regime where the radiative efficiency is not that great, and you accumulate this ICM. So this is sort of the picture. This is from a 1977 paper. So this is before the dark matter paradigm came in. So not everything in this is precisely correct, but this idea that cooling governs the range of mass in which you have galaxies was put forward in this and then even earlier papers. Okay. Now I mentioned about this feedback that not only radiative cooling, but also this energy injection by black hole accretion and by supernovae is important for governing galaxy formation. So cooling is not the whole story, and you need feedback at both high and low mass halo. So I think we have seen this figure before. What this shows in red is the halo mass function. If you just do an n-body simulation of dark matter halos and count the number of halos as a function of their mass, this is something like what you'll get. This is a power law and an exponential cutoff. If you look at the observations of galaxies, you see a curve which is shown here schematically in blue. So you have suppression of galaxies at low masses and also at high masses relative to the halos. And the answer why you are suppressing galaxy formation at low and high masses is feedback. You have supernovae which go off in these low mass galaxies, and since the potential well is shallow, these supernovae are able to blow off a lot of cold gas away from the ISM and prevent cooling and self-gravity and galaxy or star formation. Similarly, at high mass end, supernovae are not enough. Supernovae does not produce as much energy, right? If you recall, accretion is the highest very efficient source of energy production. So if you're here, observations suggest that you need AGN to pump in energy to suppress star formation. What is shown here on the right is the stellar mass to the halo mass ratio as a function of halo mass. It's essentially a similar plot, right? Here you can think of it as plot of number versus mass, number of galaxies versus mass. Here it's the ratio of stellar to the halo mass as a function of halo mass. And you see at high mass end, the mass in stars is very small. At about the Milky Way mass, the mass in stars is the maximum out of this baryonic mass. And at low masses too, you have suppression of mass in stars. And it's essentially the same picture that has been sort of shown here in terms of the ratio of stellar mass to the halo mass. And this sort of a pattern remains across redshifts. So this is actually a plot of baryon fraction as a function of halo mass. So M200, M500. So M500 is the radius within which the average density of the halo is 500 times the critical density of the radius. So this is sometimes taken as a proxy for the mass of the dark matter halo. So these are from X-ray observations. This band here, like showing WMAP, is the baryon fraction from cosmological constraints. What fraction of the matter is baryonic? You may have heard that only 5% of the mass energy in the universe is in baryons. About 30% is in matter. So 25% is in dark matter, 5% in normal matter. So this is that 5 by 30, 1/6. Okay. So if you add up all the stars in the ICM in a galaxy cluster and group, so galaxy clusters are 10 to the 14 to 15, lower mass halos are called groups. 13, 14 or 12 to 13 and a half is groups. And if you look at the accounting of all the baryons as a function of halo mass, it more or less comes close to the WMAP number. Okay. And the interesting thing is, if you separate these baryons out into stars and the ICM, you see that as you go to more and more massive halo, higher fraction of baryons are in the ICM, in the diffuse gas. So clusters are roughly closed boxes. Essentially they have almost all the baryons which were there at the cosmological epoch. They are like closed boxes. Whereas small mass halos have lost, like Milky Way has lost most of its baryons beyond its M200 or M500. Like this is the same plot actually done over a much larger mass scale. So this is written in terms of the circular velocity. But remember this scaling relation, right? M is proportional to V cube. in this cell-similar scaling. So you can actually use velocity or mass. So here I've actually shown the masses. So this is where the halos were baryonically closed. Right? This was like the figure. The previous figure was in this regime that I was showing. Now, if you go to lower and lower masses, you see that the baryonic fraction becomes smaller and smaller. This is basically looking at this end here. So most of the baryons are actually missing. We cannot account. They are so diffuse. The atmospheres are so diffuse that it's very difficult to detect them. Basically, star formation or AGN activity has pushed out these baryons from the galaxy and even beyond the halo. Most gas is in the hot, difficult to observe phase. And in order to form stars in a galaxy like Milky Way, for example, if you look at the Milky Way interstellar medium, if interstellar medium was the only cold gas reservoir and you let the stars form at the current rate, all that ISM will get exhausted in a couple of giga years, which is very short. I mean, at least short compared to the Hubble time or the age of the galaxy. What it means is that the ISM out of which stars are forming must be replenished somehow. And that replenishment happens from this diffuse atmosphere. So some gas from this cools and condenses on the disk. So there's something called a cooling flow problem. So I mentioned cooling is an important ingredient for galaxy formation. Okay. So how do we know that feedback is also important? So this is evidence for that. So this is a well-known problem in galaxy clusters, the cooling flow problem. So once you measure the density and temperature profiles of a galaxy cluster, a nearby galaxy cluster like this, temperature profile is not shown, but you can measure it by the procedure that I outlined. So once you have N and T, you can measure T cool. That's nothing but 3/2 NKT divided by N squared lambda. You can make a profile of cooling time as a function of radius. Okay. What you see is in a bunch of galaxy cluster, the central cooling time can actually be as short as 100 mega years. 100 mega years is a short time because the age of these galaxy clusters is essentially the Hubble time. They're cosmological objects. So what it means is that all this gas that's sitting here should cool very rapidly and form stars. Okay. But do we see such intense star formation? If you calculate the cooling rate of this gas, it should form stars at few hundred solar mass a year. That's like a massive starburst. But you don't see massive starbursts in galaxy clusters, in such clusters. So I think this is one of the nearby clusters. The star formation rate is tiny in this galaxy cluster. So although, so this problem is called the cooling flow problem. That the radiative cooling is very important as seen by X-ray emission, but it is not forming stars at the commensurate rate. What's going on? This is the cooling flow problem. So the answer, let me tell you the answer, what's going on, and then I'll argue why that is the answer. So the answer is that there is AGN activity at the center, which pumps in energy to compensate for these cooling losses. So essentially what happens is, although this plasma is losing energy, its temperature is not dropping because that energy loss is compensated by heating due to AGN feedback. Okay, it's sort of like if I give you a cup of coffee and if you wait for 10 minutes, it will come to room temperature, right? But if I give you a cup of coffee and tell you that, here you have it, and if you find it to be hot, that means it was on some sort of a flame within a time which is not that far in past. So in the same way, this is sort of a thermodynamic argument of that kind. Now, there are multiple evidences. There is no massive starburst in these galaxy clusters, but if you look at soft X-ray spectra of these galaxy clusters, 3 of those are shown here. If all this gas in this dense core, which has a short cooling time, if it was all cooling to lower and lower temperatures, you can predict what line emission do you expect in X-rays. So the green here, green models for the X-ray spectra for these galaxy clusters are shown here. Green is the model if the gas were just continuously cooling. So it will start at say 10 keV and then cool to 1 keV, 0.5 keV. Once you cross 1 keV, all those lines get excited. So I showed you that apex spectra. At lower temperatures, you have a lot of these lines. If all that gas was cooling through lower temperatures, you should see a lot of these lines. But these spectra do not show any of these lines. So what it means is that only a small fraction of this gas is actually cooling to low temperatures. Okay, so this is what the evidence for cooling flow is. So the X-ray luminosity is nothing but the thermal energy of the plasma divided by the cooling time. And if all this plasma is cooling and cooling, then the mass cooling rate, the rate at which the mass cools, is related to the luminosity in this way. This is called a simple cooling flow model. So you know the cluster temperature, you know the X-ray luminosity, you can actually calculate m dot, right? Kb and MP, all these are, you know all these. So this is a measurable quantity, X-ray luminosity of the cluster. The cluster temperature has been measured by those profiles. So you know m dot, and the observed m dot is almost always a factor of 10 smaller than this estimate. Okay, so this is another reflection of the cooling flow problem. This is yet another reflection of the cooling flow problem, but now this time from galaxy formation semi-analytic models or simulations. So these are some semi-analytic simulations which are trying to produce the abundance of galaxies. The x-axis is luminosity or the mass of a galaxy, y-axis is the color of the luminosity. So if, and these are like, tens of thousands or millions of galaxies in your semi-analytic galaxy formation simulation. So what you expect is a lot of these massive star-forming galaxies if there is no central heating, if there is no feedback. And so most star-forming galaxies in the universe, or the most massive galaxies in the universe in this scenario, would have been star-forming disks. But the reality shows that most massive galaxies are red and dead, elliptical galaxies. So if you put in this feedback prescription, you suppress these massive blue galaxies, right? Here all these are missing here because of feedback. This is another way of looking at it. This is luminosity function as a function of luminosity or mass. If there was no feedback, there would be a lot of these galaxies as quantified by this luminosity function at high masses or high luminosity. But this is not what is observed. Observations are shown in these symbols. If you put in this feedback recipe, then you are suppressing star formation or galaxy formation at high masses. So you get this to match. Yet another evidence that there is heating happening in galaxy clusters. So this is a composite image of a galaxy cluster showing in blue X-ray emission and in sort of magenta radio emission. And just by eye, you can actually see that there is a deficit of X-ray emission at these locations where the radio jets are. It's as if the radio plasma is just displacing the X-ray emitting plasma. Okay, and once you push this radio jets into the galaxy cluster, right, you are stirring the galaxy cluster, you are putting energy into this intracluster medium. Okay, and if you estimate the power, the mechanical power required to blow these cavities, right, the cavities have some thermal energy, and there is a PDV work that's required to expand away the gas, to displace away the gas. If you calculate that by doing a crude estimate, what you find is that this power put in by these galaxy jets, AGN jets, is enough to balance the radiative losses. The power due to these jets is roughly of similar magnitude as n squared lambda dV. That's the total losses. N squared lambda is energy loss due to radiative cooling per unit volume per unit time. If you multiply it by the volume of the dense ICM, you get energy loss per unit time. And if you take care of this, if you calculate the power work done by these jets, it's about the same value. What it means is that this is an evidence for power injection by AGN jets. So this motivates this feedback again. This is Perseus cluster nearest cool core cluster. Again, the same thing. So you see these radio jet contours. These are radio contours in Perseus, and this is X-rays. So wherever there are radio bubbles, there is lack of X-rays. So these are bubbles in radio, but cavities in X-ray, deficit in X-ray. This is Perseus again. These are radio cavities. There is deficit of X-ray emission here, wherever there are bubbles. So this is all about AGN feedback. Like why? I mean, I gave you arguments that why feedback is so important. Feedback solves a lot of problems. It prevents gas from cooling through soft X-ray emitting temperatures. It prevents massive disk galaxies. And there is direct evidence for bubbles and jets which have enough power to balance out cooling losses. Galaxy clusters also emit in radio. So these are 3 examples of radio emission from galaxy clusters. So this is like a very large scale. It's about this. The size of this is a couple megaparsec. This is a very large structure called a radio relic, and this is supposed to happen if you have a collision between 2 galaxies in a cluster. So this is like a shock where electrons are accelerated and they emit synchrotron radiation. So you can actually see it here. In addition to these relics, which are like at the edges of the clusters, you have this diffuse radio emission called radio halos. Okay, so these are associated with the cluster, with the gravitational structure of the cluster. Here is an AGN. This is a radio galaxy. This is a galaxy which is moving through the Perseus cluster, and as it is moving, the dense intracluster medium is shaping the appearance of the radio jets. Right? It's sort of getting this galaxy is moving in this direction, and that those radio emission is getting combed in the wake. There are other things also happening in galaxy clusters, something called ram pressure stripping. So if you have a spiral galaxy which is just falling into a galaxy cluster, it runs into this intracluster medium. It's sort of reasonably dense, and as this galaxy cluster is moving in, as this galaxy is moving in, it is encountering this rho v squared ram pressure, and that can strip away matter from the interstellar medium of this galaxy. Okay, and once enough matter is stripped, it can convert this disky star-forming galaxy into a red and dead galaxy. As soon as all this gas is stripped off, it will no longer be able to form new stars. So it will just have old stars because the gas has been stripped away and has been subsumed into this intracluster medium. These are 2 examples in the Virgo cluster. These are H1 contours. You can actually see the H1 has also been combed in the direction opposite to the motion of this galaxy. This in color or in brightness is H alpha emission. Star-forming gas emits H alpha. They are sort of like these Stromgren spheres, radiatively excited regions around young stars. Similarly, this is another example where you see distorted H1 profiles. So this is H1, this is optical, this is in X-rays. So this is a galaxy cluster. If you look at this guy here, this is how it looks like. So this is a galaxy, and these are bright X-ray emitting tails of this satellite galaxy. In fact, so I think it's a composite image. The magenta color is H alpha, and this is soft X-rays. So you see these long ram pressure strip tails. So this is the environmental effect of galaxy clusters, right? I told you about this morphology relation of galaxies, that if they are more and more likely to be red and dead ellipticals if they are in dense regions like galaxy clusters. So this is what converts a disk into a red and dead galaxy. So this is a model. Actually, this is a model that we came up with. This is a model for the electron number density as a function of radius for different halo masses. Now, this is a more massive halo, like a cluster. This is our Milky Way mass halo. So this is based on a model which takes care of this interplay between cooling and gravity. So what it says is, because of efficient radiative cooling, you cannot have more than this density in the low mass halos. All this matter that would have been otherwise there in absence of radiative cooling is available for forming stars, right? So basically what this shows is the breakdown of the self-similarity assumption, right? I told you that galaxy clusters are self-similar. That is, the number density as a function of R is more or less the same. You see, it's not actually true in detail. The number density for lower mass halos is actually much lower for the baryons, okay? And that's because of this radiative cooling. So here in low mass halos, the radiative cooling is very efficient. So a lot of this gas cannot be held in this hydrostatic, slowly cooling atmosphere. A lot of this has to drop out in star formation and other things. So ram pressure criterion. Okay. So if you have a galaxy like this, and it's moving through the galaxy cluster at some velocity. Okay. So if you consider a fluid element, somewhere here, right? So if you have a uniform density, if you have sigma star as the mass density of this disk, right? The acceleration due to gravity, right, is just 2 pi sigma star g, right? It's constant if it is an infinite disk with mass density sigma star. Just like a capacitor, if you have a charged metal plate, a big charged metal plate, electric field due to this nearby is constant. It's just sigma by 2 epsilon naught. So it's the equivalent answer for a disk, for a massive disk. So this is the gravity that's sort of holding this gas. So this is the gravity acceleration due to gravity, and so this is sigma g times g. This is the gas surface density. That's just 2 pi sigma star sigma g times capital G. So this is force per unit area, and this is mass per unit area. Mass times G is force, and so sigma times G is force per unit area. This is force per unit area due to stellar disk, which is holding it together. This is the force that's preventing the gas from flying off. This is the gravitational force per unit area. Now you have this, there is this ram pressure, which is given by rho ICM v squared. If this guy is moving with velocity v relative to the gas, right? That's also, so P ram pressure, that's also rho ICM v squared. If this exceeds 2 pi sigma star sigma g, then your gas disk will get stripped, right? Basically, the force which is the gravitational force which is holding the disk gas together will be overwhelmed by this ram pressure, which is trying to just take this gas with it. Okay, so this is the ram pressure stripping criterion. When does this criterion get satisfied? If the ICM is dense and if the velocities are large. These two conditions are satisfied in a galaxy cluster. Right? I showed you that the massive clusters have the highest intercluster medium density, and the velocities can be as high as few thousand kilometers per second. So that's why ram pressure stripping is very common in galaxy clusters and less so in lower mass galaxies. Okay, I think with that we'll end.